Right, okay, welcome back. I'm truly excited to introduce our next speaker. This is a person who had a profound impact in this conference. And in fact, if it was not because of him, this conference probably would not exist in the first place. And most likely also none of you will be doing any research on reinforcement learning. So Andy Barto is widely recognized as one of the founding fathers of reinforcement learning, as you may know. Most of you, in fact, probably learned about RL by reading the book that Andy and Rich wrote on the subject. So a few years ago, Andy received the Neurosciences Lifetime Achievement Award. Okay, and at the time, the organizers of that event, they invited many leading researchers from many different fields, from reinforcement learning, machine learning, psychology, biology, you name it. And they were asked to write about Andy's contributions to their own fields, to their careers, and to science as a whole. So although I could try to summarize Andy's contributions and accomplishments, I'm not going to do that. Instead, I'm going to directly quote what several of these leading researchers said about Andy when they were describing him. So this is what one person said. It's not too strong to say that Andy created the fields of modern reinforcement learning. Andy is a researcher that was far ahead of his time. He formalized and began solving challenging learning problems long before machine learning was even recognized as a discipline. Without Andy's foundational work, several of the greatest, most visible achievements in modern machine learning would not have been possible. And then a different person said, Andy and Rich Sutton created a new field of AI, of course, but they have also defined computational neuroscience. Reinforcement learning is not only a key idea for training computers, but it's become one of the most successful and impactful theories in neuroscience. And the CD learning algorithm, for example, is now the foundation to understanding dopamine signals in the brain and how animals learn from rewards. And then a third person said, Andy created all of these fields partly through his research. However, a field's success is due to more than just its research output. And then this person said, as I've grown older, I've gained a deeper appreciation of Andy's contribution in setting the tone of the field. That tone is an emphasis on scholarship, humility, and openness, on welcoming all fields and all people for whatever contribution they can make. And finally, this person said, and first and foremost, Andy is a really nice guy. So Andy, we're incredibly happy and honored that you accepted to be here to share your story and the history of the field that you have created. So with that, let's all welcome Andy Barto.
Thanks, Bruno. It's great to be back in Amherst and UMass. It's been a long time, and seeing a lot of friends and seeing such enthusiasm for RL is quite amazing. So, and I guess I want to begin by just congratulating the organizers of this. It's very meticulously organized, a very complicated first conference of this description, and it's people have done an impressive job. So I want to congratulate all the organizers. And so the organizers invited me to give a talk, and I didn't accept at first because I've been retired for 12 years or something, and I don't have any cutting edge thing to say. In fact, I don't even know what the cutting edge is anymore. But I said I could talk about some history. Would people be interested in that? And they said yes, because a lot of people don't know the origins of some of this. And so this is history. A little bit more maybe, but and the title I came up with, that'll be why that title will become apparent in a while, but I'm going to start with just my personal experience, and then look at some more historical things. So to begin with, to me, this is sort of my personal view of what RL is. It's a combination of search and memory. So trial and error, generate and test, variation and selection, whatever terms you want to use, is search. I'm thinking of search in the AI sense of search, and memory. Remember what worked best up to that time in each situation, and start from there the next time. So RL is about caching search results. So you don't have to keep searching, or at least you don't have to repeat the same elements of the search. And so another name for this would be memoized search. And if you're familiar with that term from AI, actually Robin Popplestone, who was a faculty member here, I think came up with that term. And in fact, it's memoized contextual search. It's not just one search, it's collection of searches in different contexts. So to me, that's sort of the base line of my thinking of what RL is. So it's been developed in lots of different directions, but this is kind of how I've always thought of it. So some personal history of me. Okay, I should add the generator and the tester both should be smart. So that's a key thing. And there's another, the whole history here is only one part of the history. So I'm going to be talking mostly about the actor, choosing actors, but the tester is a whole other history involving optimal control leading to TD algorithms. I'm going to not get into that line of the history. Rich should do that because of the connections to those areas. So this is part of the history. But and a key thing is trial and error, as that term has been used, is not the same as error correction, and it's confusing at first. And typically, the error is a signed error. It's much more informative than a reinforcement signal or a reward signal. So that's a key thing. So let me start. This is I was a graduate student at the University of Michigan way back, and I was a member of this research group called the Logic of Computers group, and the key personnel were Arthur Burks, who was an electrical engineer and philosopher, and actually he completed a book by von Neumann on self-reproducing automata, the very distinguished professor there, and John Holland, who's well known as the originator of genetic algorithms. And Bernie Ziegler, who was my advisor, was studying what he was modeling, the process of modeling, how you simplify models and so on and so forth. So the key subjects that were prevalent among that research group were cellular automata, genetic algorithms, and theory of modeling and simulation. So my thesis was a combination of cellular automata and modeling and simulation. It was called, I forget what it was called, but so that was the University of Michigan. I was an undergrad there too. I majored in math, and as an undergrad, I heard about McCulloch and Pitt's neuron-like units, which were logic gates, and that they formed a logically complete set of logical primitives. And that was tremendously exciting to me, this connection between the brain or biology and math. And it was like, wow, I wanna get involved in this. So I joined this group, and it was, and Holland, of course, very charismatic guy, and emphasized that genetic algorithms didn't, they weren't gradient following methods. They were stochastic. They did not get stuck on local extrema, and so on and so forth. So it was a very, very kind of interesting environment. Then I heard of a postdoc availability here, and the title was Goal-Seeking Components for Adaptive Intelligence. This was 1977, and the principal investigators consisted of Michael Arvid, who's a professor here. He's written lots of books. I'm sure you've heard of him. Bill Kilmer, who actually worked with McCulloch on a model of the brain's reticular formation. And Nico Spinelli was a neuroscientist or actually an experimentalist. And so this group of PIs, I heard about this, and in those days there were not, nobody was studying neural networks. It was unfashionable in the extreme because, well, for lots of Minsky and Papert, of course, said that that's a dead end, and so it was. But I was interested in it, and I drove up, and they hired me. So, and the source of their grant was actually a contract, and it was to explore this idea that Harry Clough had come up with, and he was a senior scientist with the avionics director at the Air Force Office of Scientific Research. And this contract was with the Air Force. And it was to explore this idea that Clough had, that neurons are individually hedonists that work to maximize some local analog of pleasure while minimizing some local analog of pain. And it's a pretty crazy idea, that neurons are hedonists, and this contract was to, is this worth pursuing? Did it make any sense? And so that's what we were doing. And his hypothesis in particular was that synaptic plasticity implements a law of effect, this term from psychology. And in particular, when a neuron fires an action potential, all the synapses that were active in contributing to that potential became eligible to undergo changes. They didn't change efficacies then, they became eligible. And if the action potential is followed with an appropriate time period by an increase in reward, the efficacies of all the eligible synapses would increase and decrease in the case of punishment. And so Clough's idea of what the reward was, what was, I forget, but we changed it. I mean, his idea was it was the membrane potential. And we created a separate signal, a reward signal, because it didn't seem to work with using membrane potential, both as the source of activation and also as a reward signal. So, so that was the task of this. This is learning by trial and error, which is instrumental or operant conditioning in terms of psychological theories of learning. So synapse, and the idea was eligibility was a number in the presynaptic terminal, and that somehow it was implemented by in terms of calcium concentration or lots of different possibilities, and that their time course of eligibility, according to Clough's idea, was that it takes various amount of time for the consequences of an action potential to come back to the neuron. And he hypothesized it was like 500 milliseconds, so it's kind of the usual time, but there's a histogram of return times, and that the trace of eligibility should look like that histogram. When we worked with this, we changed it or simplified it to just as an exponential decay without the bump in it. But the original idea was that it was a kind of histogram of the times that the action potential consequences would return to that neuron. And this would happen for all the neurons. So, and then there are different kinds of eligibilities, but we don't need to go into that at the moment. And then this guy showed up. You all know him, and actually, I learned from, I think, from Michael Arvid, that a condition for their funding was that they admitted Rich Sutton as a graduate student, because Rich had been communicating with Harry as an undergrad at Stanford. And so they said, yeah, well, we'll admit this guy. And so he arrived shortly after I arrived, I guess. I don't remember exactly, but he had a PhD from Stanford. And what did I write? Did a BA? Oh, you got it. He was my first student, actually. That's right. So I was a postdoc, but in '82, I became faculty. And I was Rich's advisor. And this is his group now, I think. So it's really great. He's been pursuing ideas and a large group of students at the University of Alberta. So, and he didn't look like that back then. Now, another person is John Moore, who's an emeritus professor here of psychology, and he was an expert in animal learning, both from a neuroscience point of view and from a theoretical point of view. So John was very helpful to us. We met with him and learned a whole lot. And this picture of John together with Jerry Tessaro, who of TD Gamma at some event. I think that was my house or something. But so John is still in town and pretty old by now, but he was important to our work then. In fact, the first paper that we published, and this was in Psych Review, which is very prestigious psychological, a journal. And John was helpful. He knew the editor. And interestingly, so this title, Toward a Modern Theory of Adaptive Networks, Expectation and Prediction. And it was really the precursor of TD. And the original title that we submitted for review was Toward a Modern Theory of Adaptive Networks 1. And the reviewer said, get rid of the 1, because we had in mind 2, which would have been a model-based extension of all of this, which we never did. So we had to get rid of the 1. And then, whoops, wait a minute. Then we had to write a report for the funding agency. And we wrote this thing. You can download it. It was like printed, it was like 2 inches thick. Because we were, it was a very unfashionable thing. We wanted to continue to get funded. And it was like, we had published a lot of things and it sort of collected all of this. In addition, there's some things in there that haven't seen the light of day. And so, and I think that at the Air Force, they gave it a nickname of the, what was it? It was, huh?
The yellow report.
Yeah, it was the Yellow Beast or something like that, because it was something like that. Yeah, it was yellow. Anyway, so we did get funding, and TD algorithms really evolved from that Psych Review paper, and Rich's thesis was basically on the TD algorithm. So that was very interesting days back then. Whoops, wrong direction. And then Chuck Anderson came. I don't remember exactly what year, but he had a degree from University of Nebraska, and he was my second student. And now he's at Colorado State and founded a company. And unfortunately, he's not here, but he was the second in this group and we tackled this pole balancing problem. So we wanted to do something to illustrate the fact that this learning rule was actually to be used as a controller. And someone suggested this. It was a task that was done by Mickey and Chambers, and we thought we could beat it. And we tried really hard to beat it. I thought that their system was deterministic. And I thought these neuron-like units are going to be stochastic. They have to try different things. And I thought that would be enough to surpass Mickey, but it wasn't. So we added an adaptive critic, which is basically TD algorithm. And so that pair became actor-critic configuration, and we were able to, at the last minute, to surpass the results of the Mickian chambers, and this appeared in a special issue back in '83. And Chuck wrote the code for this. So the actor-critic architecture, originally it was represented as a kind of neural network. We thought of the actor and the critic as neuron-like units, and the decoder was some kind of network that created inputs to this system. And then, as it evolved, we kind of, you can drop the neural network idea completely and just think of this as a kind of learning control architecture. And that looks like this. And the adaptive critic and the actor and a reward signal and a reinforcement signal. So we make a distinction between reward and reinforcement. So that's, not everybody does that, but I think it's important. Now, Chris Watkins, this is Rich, and Chris Watkins is Mr. Q-Learn. And so Chris was involved, and actually I was a reader on his thesis at Cambridge University in England. I was on sabbatical there. And so he actually, I think, enabled us to connect strongly with MDPs. Before this, there was no MDP. And so, but the idea of using that formalism fit very well. And, throughout this, I was always struggling to connect what we were doing to classical, more traditional engineering and mathematical techniques, mainly because I wanted to be respectable. It was not a fashionable thing to be working on, and I didn't want it to evolve into a cult. An isolated bunch of people who just talk to each other and like a cult. And there are areas that are such things, and we wanted to avoid that. In fact, we resisted creating a journal or something because we wanted to be part of the machine learning community. So Chris Watkins, and he's still actually interested in reinforcement learning. He's at Royal Holloway in London, and wonderful person. So now that's sort of the personal, that's how we got involved in what became so-called modern reinforcement learning. So this goes back to ancient reinforcement learning. So Thomas Ross, 1933, created, it was an electromechanical system that was actually a reinforcement learning system at the University of Washington. And I got this from the cyberneticzoo.com, which is an amazing, wonderful website. A lot of history, and there's pictures from that. Both pictures are from that. So that's 33, was reinforcement learning. And Stephen Smith, who actually I think was the teacher of Thomas, but he later did a mechanical rat that finds its way in a maze, and it was reinforcement learning also. So that's sort of the earliest thing. This was, machine learning. These were machines. They were not computers. They were machines. This was not a computer. It was not a reinforcement learning system either. But he did experiment with reinforcement learning a system a little bit. This was a kind of conditioned reflex turtle, and I put it here because it was just like a Roomba without the vacuum cleaner. So maybe smarter than a Roomba. I have the cheapest Roomba, so I don't know how intelligent they are, but it gets the job done. But this thing had no vacuum cleaner, so it took years to do that. Now, this is Alan Turing. This is the earliest, I think, idea of implementing RL on a digital computer. And he never implemented. But this is what he said, and if you read that, it's very much like what Clough was talking about, and it's law of effect, instrumental learning, and pleasure and pain, and I think stochastic also, if I recall. Anyway, it was not implemented, but this was, and when was it? It was 1948, when I was born. So this is Farley and Clark, a little bit later, and this is the first implemented simulation of a self-organizing system on a digital computer. And it was the first simulation of adaptive neural network simulated on a computer, and it was reinforcement learning. So actually the computer was at MIT, and it had 4K of memory. And so, you know, it was a very early computer, and they started with a randomly connected network of 64 stochastic linear threshold units, and they trained it on a task using a proficiency measure, which is basically a reward signal, roughly to make the activation of one group of neurons higher than another group. And they were able to train us to do this, and you know, it was a neural network. Now, modifier, basically, it was like Clough suggested. If a change is in a favorable direction, then all the weights which just previously participated in firing an element are increased. If, on the other hand, the change was unfavorable, those weights are decreased. Never mention of eligibility, but basically it's there. And they also say that the weights change without regard to their influence on the overall output. It was kind of a statistical cooperation that led to solving this reinforcement learning problem. So that was, when was that? 54, something like that. And then same year, Marvin Minsky, of course, we all know who he was. His thesis was the reinforcement learning system, which he built, physical system. He used these units called SNARCs, stochastic neural analog reinforcement calculators. And they were like synapses, not whole neurons. They were like synapses. And he built this thing. He said it worked surprisingly well. But he went in a different direction, obviously. And in this paper, Steps Toward Artificial Intelligence, 1961, is full of discussion of reinforcement learning. And the term credit assignment, I think, comes from Minsky. You know, there are different ways, different types of credit assignment. But, you know, of course, later he and Papert argued that, you know, neural networks are not a good way to go, and went on in a different direction. But we were heavily influenced by his work, his old work. And now Farley and Clark had a later paper, Generalization of Pattern Recognition in a Self-Organizing System. It was the same network, but it was trained with supervised learning. They forced the units to do what they should do and train that way. And they got excited because of generalization. They trained it on particular cases, but it would generalize to others. And this, to me, was the switch from RL to supervised learning. And the earlier stuff was RL. And this, they gave targets and we're excited about generalization and so on. But I think, you know, people who followed were like Frank Rosenblatt, the perceptron was supervised completely. And here's a statement. The foundations for all of this artificial intelligence were laid at Cornell, which I don't think is a valid statement. But this was Frank Rosenblatt, and it was all supervised. We all know the perceptron learning rule. And then, but Arthur Samuel's checkers player was reinforcement learning. In you know, the late 50s, early 60s, and we were students of this, and actually proposed to do it right. We didn't think that he actually did it right, but that was very influential also, and that was reinforcement learning. Then Woodrow and Hoff, Bernard Woodrow and Ted Hoff were doing supervised, and with this Adeline, adaptive linear neuron, it was the LMS algorithm, and or Woodrow Hoff algorithm, and Woodrow is still an emeritus professor at Stanford, and Hoff is credited with inventing the microprocessor. And he was in industry. And here's a picture of an Adeline where you had to turn these rheostats to adjust the weights by hand. So it was, you know, but it was supervised. It was supervised. What, Rich? You're trying to tell me something? No, okay. So later, you know, there's another paper by Woodrow and some students. Reward, punish, reward, learning with a critic in an adaptive threshold system. And this was his foray into reinforcement learning. And basically selected bootstrap adaptation was, if there's a reward, you treat what you did as the target and then do LMS. And if you're punished, you do the other action and use that as a target and do LMS. And it was deterministic, and they did blackjack and some things, and Woodrow said it's the hardest thing they ever did, and they didn't pursue it, I think. So, and of course, Woodrow done all sorts of applications of LMS to signal processing and so on. So, but this was their foray, only foray, as far as I know, into reinforcement learning. Then also we discovered work by Michael Setlin on learning automata. And he died young, but there's a book that was published posthumously that's a collection of the work there. This was in the Soviet Union. The book is called Automation Theory and Modeling of Biological Systems. And these were stochastic reinforcement learning systems, very clearly. And there's a survey by Narendra and Thatachar that came out later. And we were heavily influenced by this as well. They studied, whoops, I thought I had another thing here, but they talked about games and teams of learning automata. So a team would be collection of learning automata, but they all shared the same reward signal. And a game would be where the units get different signals, and so there could be competition and so on. So this was really interesting, and so we were influenced by this as well. Why did I put that this way? I guess I'm nearing the end. I'm going too fast. So another very exciting thing is this reward prediction error hypothesis. I mean, my original interest in all of this was connections to biological systems. And this was very exciting, this idea that the brain's dopamine system works like the TE algorithm. And this hypothesis, I think, is still a mainstream hypothesis in neuroscience about how the dopamine system works, that the dopamine signal is not reward, but is a TD error. And that makes a lot of difference in terms of how you think about how the brain is doing this. I think classically they think of dopamine as a reward. But it seems like it's more accurately modeled like a TD error. So, or a reward prediction error, as they would call it. So I've lost track of time. Okay, so a unique property of RL that I've always been interested in is that you can have a RL system interacting with anything that you don't know details of. There's a critic, there could be other influences, but learning can take place in the system without knowing the details of how this blob generates activity. And so this leads to the idea that, again, following the Setman idea, collective learning, you can train a neural network by broadcasting a reinforcement signal to all the units. It's a team problem if they're all getting the same signal. And you can train neural networks like this. And I wrote a paper when we did some experiments in 1985, learning by statistical cooperation of self-interested neuron-like computing units. It appeared in Human Neurobiology, which I'm not sure many people read, but it was a special issue or something, and I was done, and that was I was never very sophisticated about publicizing stuff because I was intrinsically motivated. And then backprop became popular due to the PDP book from Rummelhart and Hinton and Williams. And I didn't give a date here because backprop has a whole lot of history, different people going way back from optimal control, all sorts of things. So, but basically the PDP, I think it was essentially the same time that I'd been working, and I thought, wow, this statistical thing, it really works. I can train networks to do nonlinear things with layers, and it can, and it worked, but backprop came out, and we implemented it. Actually, I was on the phone with Rummelhart to make sure we'd implemented it correctly. And it's way faster. But we did, so Mike Jordan was a postdoc here. You all know Mike Jordan, who's now at Berkeley. But we did it, we could claim that we could do gradient ascent without backprop. So, but it's really slow. RL broadcast algorithms scale extremely badly as the number of units increases. You know, it's a credit assignment problem. You've got all of these things changing the reward signal, but they have to figure it out for themselves just by many, many trials. And it's a problem of structural credit assignment. And I remember at some meeting, Jeff Hinton was talking about various layered network learning algorithm. They said, well, Boltzmann learning is slow compared to backprop. Reinforcement learning, don't ask, is what he said. And he was right, it's very slow, but it's biologically feasible. And, you know, to the best of my knowledge, people have not proposed a convincing, produced a convincing story that the brain does backprop. And, you know, it requires some things that just seem like the brain doesn't do that. But the idea of broadcasting a signal like this is very plausible. And so, but it's very slow. Well, maybe that's okay. Or it's not broadcasting to the whole system. There are components. You know, if the numbers get smaller, if the number of units are smaller, it works better, and so on. So there, you know, if you're interested in what the neuroscience, what the brain might be able to do in terms of collective learning, I think this is still plausible, but of course, everything now in deep learning is backprop, right? Which does, and I guess I never liked backprop. But so now I've lost track here. So a challenge of designing reward signals. I mean, this is something that is talked about today, very much about dangers of AI, dangers of reinforcement learning. And Nick Bostrom talks about perverse instantiation with regard to reinforcement learning. And this is an old problem. It's basically optimization. And Norbert Wiener wrote about this, wrote a book called, I forget, but he gives the story of the monkey's paw as an example of how you have to be careful what you wish for. So what you wish for is kind of like, what is the reward signal? And his story is that I think it's a classical horror tale where they discover something that grants them 3 wishes. And the first wish is, well, are we going to get a lot of money? And then the next one, their son was killed in a mine accident and they got a settlement from the insurance company or something. And then the third wish was, we want our son back, keep the money. And so it was, it grants you what you wish for, not what you should have asked for or what you intend. And this is what the problem is with reward signals. You don't, or with optimization in general, you don't know what's going to happen. And in a lot of our simulations, the system would do things we never thought of. We thought, oh, it's good in terms of that reward signal, but that's not what we intended. I remember when we have this car moving around a curve in a track, had momentum and stuff like that, and it was punished if it hit the wall. And then we zero out the velocity and it would start over again. And we thought, well, that'll encourage it to do a nice avoidance of the wall. But the system came out with it would slam into the wall and then turn at 90 degrees because it was 0 velocity. And that was the optimal solution. So we said, oh, we have to change the reward fund. So yeah, it's perverse instantiation. So this is a problem with optimization in general. And engineers know about this and they deal with it. Often by, tweaking the reward signal or the objective function in optimization. And, it's not a new problem. Midas touch, that's another example of things going haywire. And also there's a wonderful movie, Bedazzled. I think there's a modern version of this, but this is an old movie, Dudley Moore, Peter Cook, where the grantor of wishes finds loopholes at every turn, and it's hilarious. But it's a classic example of how be careful what you wish for, and RL has that problem. Okay. And my students. So this is some of my students. And you can recognize many of them. Some are here. Rich is, where's Rich? Yeah, there's Rich and Chuck. That's Rich and Chuck. Satinder Singh, Robbie Jacobs, who's a professor in Rochester, Amy McGovern, who is running a big project on applying AI to weather. Oscar Simsek. This guy is here too. I don't see him, but anyway, none of this could have happened without the students. And I've been the students that I've had to work with, that I've been able to work with, are have been just astounding. And I think my philosophy of directing grad students was, I'm just interested in ideas, and I'm interested mostly in the students' ideas. I'd never say, "Oh, work on this idea." They'd have an idea, and I'd kind of steer to, get it to a point where you could actually do something. And throughout all this, I was always interested in connecting as strongly as we could to classical methods, traditional methods, well, not to become a cult, first of all, but to try to figure out what properties of reinforcement learning are really useful compared to our methods, optimal control methods, and so on and so forth. So, as time has gone on, we've gotten a more clear view of, the last panel was very informative in terms of this issue, but I've always strived to connect to existing things and say, yeah, it's like that, but it's got this other thing. And I think that's been very useful. And we're not a cult, yeah, anyway, so this was a title, and I've illustrated that machine learning was mostly RL in addition, because that was the most salient thing from psychology, Skinner and behaviorists, and it was only later that it morphed and focused on supervised through perceptron, LMS, very successful algorithms, but they kind of lost the thread of reinforcement learning. Errors, signed errors, usually much more informative than a reinforcement signal. And so we tried to make that point. So this is the source of the title, and I thank everybody for their attention, and I'm amazed at all of the developments that have come about, and but I just hope people keep the idea that the connections to classical methods are a really important part of all of this, and that it doesn't become a isolated cult. So thanks very much. That's the first standing ovation now. Wow. Okay, good. Questions? Do I have time? I don't know.
We do have 15 minutes. So do you have some time for questions?
Comments? Complaints?
So, Andy, over here, great talk. So, the loudest and clearest message you've given here is don't become a cult. Like you said, you didn't start a journal, presumably you didn't start a conference to not become a cult. But we've got this fantastic thing here. How would you advise this to continue and not to become a cult?
Well, I think it's progressed long enough over the years that it's not a cult. There are enough powerful applications, and the theories become much more sophisticated, and I think people are aware of connecting to classical methods. So I don't think there's a danger anymore. I think we're out of the woods in terms of the cult. Still a little bit of cultness, but in the early days we were, it was very unfashionable. And and AI was always seemed to be about fashion. You know, the hot topics were there for a couple of years, and then there'd be another thing, and you know, if you wanted to get grant money, you'd have to be fashionable. And we always resisted that. That's why we wrote that 2-inch thick report, because you know, we wanted to continue doing our unfashionable stuff. But now it's pretty fashionable. I don't
The first ICML conference I went to, the RL session had 3 papers and consisted of the people who would walk with Rich through the woods.
Yeah, so, no, it owes a lot to some amazing, I mean, the game results and you know, TD Gammon was that groundbreaking, not to mention Go and all the more recent stuff has been amazing. But, you know, as people pointed out here, they're very, you know, there are limitations, partial observability, and all these things are a problem that, you know, are hard to address. But yeah, I think we're out of the woods in terms of becoming caught. Maybe I'm sorry I mentioned that at all. All right, next question.
Thank you for the amazing talk. The term trial and error to explain learning occurs in late 19th century, early 20th century, and reinforcement learning appears as early as 1937 in Skinner's work and sort of the behaviorism of the time, which was later obviously debunked by a lot of cognitive scientists. There's a lot of interactions between reinforcement learning and neuroscience as well, like the Actor-critic and many other things that have homologs and inspirations from the brain. Just wanted to get some of your anecdotes or personal stories of this kind of interaction between a sort of first early 20th century type of psychology and reinforcement learning, and also perhaps between reinforcement learning and neuroscience in your own work. Would love to hear some anecdotes, to be honest.
Well, I was always trying to connect to neuroscience and operations research. And in fact, I think I invited myself to give a talk at MIT to Bertsikis's group. And you know, very well known in control theory and operations research. And I gave a talk, and then Bertsikis published a book before we did, because he writes a lot of books very quickly. that connection to Bertsikis and Sitsipas, you know, opened up a whole lot of things, and that was fruitful. In neuroscience, I've hung out with neuroscientists at various conferences and so on, and I'm not a neuroscience scientist, but I sort of appreciate what they do. And I've been involved in grants that were neuroscience grants, and it's been just exciting to interact with people in different disciplines and explaining what you're doing and using their language. It's important not to create your own isolated language. So the idea is to adopt, you know, to fit in. Maybe it's just because I don't want to be ridiculed for doing something obscure, but making it useful. So there are other fields I haven't established to economics. They're very closely related ideas in economics. And OR, of course, control engineering, neuroscience, psychology. I don't know, there may be other disciplines that could yield some connections. It was just not only the connections, but it enriched what we were doing, because they had developed these ideas and often algorithms that you could relate to or perhaps adopt. Yeah, so is that an adequate answer to your question? It was a very good question.
It's great. I would probably later ask you what specific things you might have gotten inspired by in some algorithms.
I'm sorry?
I think I'll ask you later about some specific things that you might have drawn direct inspirations in your work. Maybe.
Okay, great, thank you.
Sir, thank you for your talk and planting the seeds from which this community grew. You mentioned in your briefing to be careful what we wish for, and also caution to remain focused in part on classical methods. And my question is, what if we do not heed such advice? What if we forecast some of the ramifications?
Well, it opens you up to someone saying, oh, why didn't you use this that's been around for 30 years that does better than your algorithm? You know, and I always wanted to avoid that comment, but it's quite easy to show something using RL and some person will say, what are you doing? Oh, well, we do that this way. And sometimes that's true and sometimes it's not. So I guess, yeah, I don't know what else to say. Does that help answer what you're after?
It does.
Okay, thanks.
Thank you.
I really appreciated your historical perspective. Sorry. I really appreciated your historical perspective on the field. And I think something that surprised me and probably a lot of the younger acolytes was just when the Markov decision process entered your radar. So I'm wondering, could you say a little bit more about how it changed your thinking and how you thought about reinforcement learning before you started thinking about MDPs?
Yeah, so that was a late, you know, we had no idea about, we weren't thinking about sequential decision problems, dynamic programming, other classical techniques, and they came in slowly from reading and then Chris and others, Chris Watkins' thesis was dealing with. So you know, we kept our eyes open for related methods. But in the early days, you know, it was mostly neural networks, which was why I got interested in it, because you know, McCulloch and Pitt's idea of the, you know, the mathematical view of what neurons are doing, and so that's been persistent. But it sort of changed, you know, it moved away from neural networks and became a more algorithmic approach. Yeah, MDPs, yeah, we became aware of those. It was like, oh yeah, this is really a good way of formalizing what we think these algorithms are good for. And so, you know, that was from reading books and then having Chris and others contribute, you know, ideas for that. But you know, I always kept my eyes open for. So I was wondering, you know, we have these algorithms. What are they doing? You know, what's the mathematical way of thinking about what these algorithms are doing? And you know, that leads to creating a formalism that you can say, oh, they're doing this, and then trying to find other algorithms that are dealing with the same types of problems. I guess, I mean, in some cases, students will write programs to do something, but you don't know what they're doing in terms of some more general framework. And I think I always strive to put things into a context, mostly a mathematical context, so that we could know more precisely what these things are doing, what they're good for. I haven't always been successful doing that, but that's still, you know, of course I've been retired for a long time, so I'm not actively doing this, but I observe what's going on. And yeah, so is that a good answer?
Love it, thank you.
Okay, thank you.
Andrew, thank you so much. I feel honored to be
Oh, thank you.
and also thank you for all the tangible and intangible value that you have put.
I can't hear you.
And thank you for all the tangible and intangible value that you have invested into this field. I wanted to ask, what struck me is the closeness of connection of, again, which we know, but still, of the founding of reinforcement learning and kind of this early 20th century philosophy and psychology ideas, right? And I'm curious how you feel. I feel that since then, actually, those fields have evolved a lot of their understanding. And I'm curious how you feel if reinforcement learning can kind of broaden as a result and try to mathematize, to continue to try to mathematize that relationship. Or it's good as it is, and it's without becoming a cult, of course. Or it's good as it is if it continues first. Sorry, that was very confusingly phrased.
Yeah, so I think in the way of answering this, I mean, most of what we were doing, we were not modeling animal learning. We were borrowing from what the animal learning theorists had worked on, but we were building systems. We were building algorithms. And in a few cases, we were trying to model animal learning. I think that first paper in Psych Review was modeling classical conditioning. And the TD algorithm was a novel extension of the one model that the psychologists were using. But mostly we were not, we had our eyes on that literature, but we were not trying to model animal behavior. Of course, it was extremely suggestive. Latent learning, model-driven reinforcement learning, a lot of these things were suggested by what psychologists had been talking about for years. But we were computer scientists, not psychologists.
I'm asking whether you think we should continue to keep an eye, because I think the thinking in those fields has really evolved.
Yeah.
And our models are based on that older understanding.
I mean, it's hard to keep up with all of these different fields, but it would be great to try to do that. So, thanks.
Thank you.
Hello, Andy. Thanks for the great talk, and thanks for laying down the foundations.
Thank you.
Yeah, so I have a question about your opinion about alternatives of backprop. So you just mentioned that in the beginning, machine learning was reinforcement learning, and I think there are a lot of ideas other than backprop, including the ones that you just mentioned. I just wonder if you have more thoughts about what are the possible alternatives to backprop.
What are alternatives to backprop?
Yes.
I'm not a scholar. I mean, there's so many different methods have been proposed. Perturbation methods. I mean, the RL approach is basically perturbation methods, and some methods perturb the weights, and some perturb the output of the units, which is what I was interested in. You can also perturb the weights. And, it's a stochastic search through perturbation, and that's kind of a classical approach. So, these are alternatives to backprop, but backprop doesn't, computes the gradient very directly rather than estimating it from samples. So that's very fast. And lots of people have tried to argue that the brain could do various versions of this. And I guess I've not seen something convincing. I'm not sure, but there have been lots of proposals. Oh, well, a slight change of backprop is something more plausible from a neuroscience point of view. I don't know what the latest view is, but I think even Jeffrey Hinton says, the brain doesn't do this. We do it, it's faster, it works, of course, and the brain is doing something else. Maybe not reinforcement learning. Maybe it's something else. So, there's a lot of literature dealing with this. So, is that?
Yeah, so I guess I'm particularly interested in knowing your opinion about the collective learning idea that you just mentioned, that this error signal, TD error signal,
is passed to all the neurons. And how do you think about that idea?
I didn't get your question. I couldn't hear
Oh, sorry. I was saying that the collective learning idea that you mentioned in your talk. So I'm interested in knowing your opinion about that way in particular. Sorry, I didn't make that explicit before. But do you think that is like some valid way that can achieve either like a comparable or a better result than backdrop?
I still don't understand what you're asking. When you mention a learning method, you mean a broadcast reward signal?
Yes, exactly.
Yeah. Have people tried to relate this to neuroscience? For the same experiments, and it's much faster. So his thesis is interesting like that. It was actually using layered networks trained by reward signals to do pole balancing and a couple of other tasks. But backprop is just really, if you really want to do this without connecting to neuroscience, backprop is a better choice. There have been, I don't know. I'm not completely aware of all that literature. But other people have talked about reinforcement like algorithms and in terms of neuroscience, that there is a plausibility there. And we know that signals are broadcast. The dopamine signal, if it's a TD error, is broadcast to wide regions. And the dopamine signals, there's not just one dopamine signal, so there's many. And so it may be multiple learning systems using different parts of the whole neural network. So I'm not up to date on that, but it's a very interesting thing to look into, I would suggest. So, yeah, thanks.